Let's look at one application now. This is some where we're going to start to see how this whole machinery will actually become very powerful. What we're going to do is we're going to figure out a way of computing the distance from a point to a line, and we're going to do everything in 2 dimensions to keep it simple, although what I'm going to show you can also be done in 3 dimensions, leading to a formula which is pretty much the same. But this is the idea. So the idea is, all right, let's say we're in the xy plane. We have a point which we're going to call x0, y0. And then, oh, by the way, in linear algebra, if you haven't noticed yet, there is a lot of importance placed on notation. So make sure that you're familiar with the notation. If you're not, play with it, but make sure that you can understand what the notation means. Okay. So x0, y0 just means the 0 just means it's a starting point. Okay? And we have some line. Let's look at the general equation of that line. I'm sure you remember that from high school. So general equation is going to be ax plus by plus c for some numbers a, b, and c. All right. Notice that this line has slope minus a over b. Well, that's if b is not 0. If b is 0, we're dealing with a vertical line, and it's a special case, but what we're going to find out works even in that case. Okay. So let's assume that the slope is negative a over b, and what we want to find out is actually what is the distance, that means of course the perpendicular distance from the given point to the line. So how are we going to do it? Well, one way we can do it is we can construct the equation of the line, which is perpendicular to the given line and goes to the point x0, y0, then find the intersection of that line with the given line, and then use the distance formula to find the distance between those 2 points. That's a fairly lengthy procedure. There's another way of doing it that involves calculus. One thing we can do is we can figure out what is the distance between x0, y0 and the generic point on the line, and then look for the minimum. Of course, that's going to be the distance by definition. That one is also going to be fairly lengthy and involves taking derivative, doing a first derivative analysis, and so on and so on, basically solving an optimization problem. Okay, we're going to do it in a slightly different way, which will be we'll use all the techniques that we've seen so far, and will give us a formula which is very elegant and very simple at the end. So what are we going to do? First of all, we know that the slope is negative a over b. So let's say that we draw a segment, a horizontal segment of length b. Okay, we're going to think of that one as the run of the slope. Okay, so corresponding to that one, the rise will be equal to negative a. So that means that once I've drawn these 2 segments, one is along b, the other one is along negative a, then the vector that basically forms the hypotenuse of that triangle is going to have components b, negative a. B is the horizontal one and negative a is the vertical one, right? So we're going to keep all these things in mind as we move on and try to compute the length of that blue segment. So how are we going to do that? Well, first of all, notice one thing. If I take the dot product of this vector b negative a with the vector ab, well, what is the dot product? It's going to be ab minus ab. Well, that's equal to 0, right? So what that means is that the vector ab is going to be perpendicular to b negative a, which means that the vector ab is going to be exactly along the direction of the blue line. Possibly longer or shorter, we don't know, but it's going to be along the same direction. Well, we're going to make use of that fact. Now, what we're going to do is we're going to pick an arbitrary point on the line. Well, this is sort of what we would have had to do in the calculus approach to solving the problem, but turns out to be a lot easier than that. So we pick a point PQ on that line, and we're going to consider the vector that joins the point PQ to the point that we started from, x0, y0. Now notice that PQ is the tail of the vector, x0, y0 is the tip of the vector, therefore we can figure out what the vector's components are, namely x0 minus p as the first component and y0 minus q for the second component. Notice I'm using the combine there. Remember, it's an alternative notation. I'm just, because the notation for this vector is getting longer, I want to make sure that we distinguish where one ends and the other one begins. All right. Now let's look at that picture. What are we after? We're actually after that length of that segment D. But what is that D? Well, that's exactly the length of the projection of this new vector x0 minus p, y0 minus q, the green vector, onto the vector AB which is along the blue line that we were considering. Okay, so what we're going to try and do is compute the length of this projection. Well, this is a scalar projection, right? So what we can do is we can use the formula for the scalar projection. So that means that we have to take the dot product of those two vectors, x0 minus p, y0 minus q, and ab, and divide that by the length of the vector ab on which we are projecting. Well, let's do that. If we take the dot product on top, we end up with, well, I'll let you do the algebra. You want to pause it for a second to make sure it works. And then on the bottom, you have just the length of that vector is going to be the square root of a squared plus b squared. Okay, that looks a little bit still messy, but this can become a lot easier because look at those two terms, minus ap minus bq. Now remember, we chose the point PQ on the line, which means that the coordinates P and Q have to satisfy the equation of the line, which means that AP plus BQ plus C is equal to 0, which means that C is going to be equal to minus AP minus BQ, which is what we have in that formula. So that means that the formula can actually be simplified to this form. Absolute value of AX0 plus BY0 plus C divided by square root of a squared plus b squared. And that is the formula we're after. Once again, notice that we've gone through a number of steps, some of which probably you may want to see again, just to make sure you understand how they were done. But all we used was just projections and dot products. And what do we end up with? A formula that gives us the distance of the point x0, y0 from the line ax plus by plus c equals 0 in a very elegant way that just reflects those two formulae. So on the top, notice that we have the absolute value of what looks like the left side of the equation of the line, except that we're putting the coordinates of our point in there, and then we're dividing just by the square root of a squared plus b squared. Yeah, so it's a fairly simple formula. As I said, it can also be generalized to 3 dimensions. In 3 dimensions, of course, you will have an ax0 plus by0 plus cz0 plus d, and in the bottom we're going to have the square root of a squared plus b squared plus c squared. So it's going to be longer, but not any more complicated. And again, this is one of the beauties of linear algebra, the possibility of extending, generalizing, and looking at a general structure that holds even for complicated situations.